We're going to get into the addition of vectors now, which is another step forward towards the AC theory that we're working towards, and some of the rigging concepts we'll go over later too. So again, we're going to be talking about total displacement, like we mentioned what that is in the previous recording. And they got a little diagram over here in figure 3.22, and they're just kind of demonstrating down here that both of these are equal to the end destination, or the resulting vector, which they're calling r, which is this hypotenuse right here, if you will, of this direction. But also any other combination of vectors can get you there. As long as that's the end destination, the resulting vector is going to be the same whether we're talking about a plus b plus c plus d, or if we're just doing e and f, which is just a north and east movement. So we got a magnitude of 3 blocks on b east, then 1 block north c, then we have back west 1 block again, and then 2 more blocks north. Those are all individual magnitudes. They give us a total displacement of 3 blocks north and 2 blocks east. So they're just showing you pretty much that the vectors you add up, it doesn't really matter what the totals are. It's just where you wind up, your end destination. So r is really just the point-to-point bird's eye view. If you were to fly as the bird flies directly to your end destination, that would be the resulting vector, no matter which method you use to get there. Now down here, they're going to talk about using the graphing method for solving this, which is pretty much just getting like a ruler and setting up a scale to solve it. That's not really going to help us out when we move on to some of our other concepts, so I wouldn't focus on that too much. You can see here they're talking about how many centimeters are going to count for a mile. Don't worry too much about this unless you want to learn some extra skills. We're only picking and choosing the ones that we're going to carry forward into the later concepts we're going to learn. So let's look at figure 3.23 here. So they have a 20-mile magnitude in the east direction, which it completes us one vector, which they're going to call this vector right here at 90 degrees. And then over here we're going to add a 30-mile magnitude north, and that's going to be an additional vector. So these are two, and if we had this on an XY chart, an X and a Y coordinate, or in this case an east and a north coordinate, that add up to a resulting vector point right there. But if we look down here, now they're adding C. Now C here is different than A and B. It's not in a single direction. It's in a combination of directions. So this is actually backtracking a little bit from our east direction and our north direction, and it's going slightly south and west. So our resulting vector from these now would be right here. Now we're going to be looking at these a lot differently, but the concepts are all going to be the same. So later on when we have our XY charts, we're going to be considering all of these vectors, whether it's A, B, or C, not stacked on top of each other's tails like they are here, but they're all going to start from the same point of origin, which will be 0, 0 on our XY chart. So later on it's going to look something like this with the 20-mile, and then from the origin as well, now you're going to have another vector from the same point. This is going to be your 30-mile, and then we'll have another vector, which is C in that other diagram, which will be something like this, and that was our 10-mile magnitude vector. So just understand that written like this or this, no matter which way we view it, they're going to have the same resulting vector once we add them all together. And we'll see what the technique is for adding those together next. But we'll get more comfortable with looking at them like this soon, but a lot of the book, it's going to kind of lay it out like this method. So expressing the x and y components as assigned numbers, we find the resultant vector of several vectors as follows. So these are some steps you're going to want to read here, and I highlighted those just so you guys can take some time to go through them. But they're just talking about how to break down the vector into individual x and y coordinates, and then based on what those numbers are, you're going to get a sign. So if you're going in the negative or positive direction, you're going to get positive or negative units for each of these. So here we have 3 different examples. So we have A and B here, and the resulting vector is going to look something like this by adding those 2 together. So our example they have here is right there. So 3 plus 2, and you can kind of see you're going to give you 5 in that direction. So this would be your overall resulting vector. Now you can't add the magnitudes together unless they're exactly in the same direction. Exactly, which is almost never. So if you have one that is only an x value, which if you look at figure B here, we have 5, you can't add that to 6. One is an x coordinate and one is a y coordinate. So first we would have our 5 movement here with 0 movement up or down, and then we would have our 6 magnitude movement up with 0 movement left or right. Now to put that a little more simply, we're just going to find out the coordinates for where this ended. So down here on this chart, this 5 magnitude vector, the end coordinate was 5, 0, because we had a 5 magnitude movement on the x-axis with 0 movement on the y. This next vector has its complete own set. So it's going to have a 0 movement on the x and a 6 movement on the y. And when we add those 2 together, 5 plus 0 is 5, 0 plus 6 is 6, we're going to get the resulting vector coordinate here. Now if these were going down or left, you may get negative values for some of these. And it's going to show you a little bit below that you need to make sure you factor those negative values in to get your overall resulting vector, because some of the directions are going to be opposite of each other and they're actually going to cancel out, which would subtract some of their magnitude. So in this case, this is probably a little bit better example, but you're going to get your coordinates for A, which is 7 and 2. So we come over 7 and up 2, and that's where we ended. Now this coordinate here, we're going to add in to our values here. Then B, we move the opposite direction. So we move negative 2 on the x and positive 1 on the y. Here you can see negative 2, positive 1. Then for C, we move another negative 1 on the x and then a positive on C, which is positive 4, which is the negative 1, positive 4 you see here. Now if you add these values together, you can see you get 4, 7, which is where we should have ended up, whether we stacked them up or solved it using another method. So if we come over 4 and travel up 7, you'll see you would have wound up in the same place. So that 4, 7 coordinate was where you wound up, whether you were adding them like this, their coordinates, or whether you were just stacking their tails on top of their origins to see where the endpoint would be if you had a nice clean graph. So again, they show you the resulting vector, and then our 4, 7 that we got down here, you can see that a 4 on the x and a 7 on the y would have given us the same total as if we added up all of these together. We still had the same total displacement. We still ended up at the same end resulting vector here. Here's a couple more examples, and they do quite a few of them for you here. So we're mostly going to be having 2 or 3 that we're going to be adding together, but they show us 4 here. So you can expect to see something similar to this, or maybe even less complicated, and just get real comfortable doing those. So whether you had all of these stacked on the tails like they're showing you here, or whether every single vector's origin was at 0, 0, you would still wind up with the same values here. So your resulting vector, even though you had all these moves on all A, B, C, and D was really only a +4 and a -2 in the end. So we moved to the right 4 and down 2, and here was our resulting vector from all that vector addition. So the point they make here, where I have highlighted, two vectors are equal when they have the same magnitude in the same direction. It kind of comes back to the concept of it doesn't matter where on the graph your vector begins and ends, it's just the magnitude that matters. You can see that A and B here aren't next to each other or on top of each other, and neither of them start at the origin, but there's still the same amount of force or energy or direction or distance, whatever the magnitude is, of total movement. So they would still displace an object the same amount no matter where they were. And you can see here that C and D are actually opposite from each other. They would cancel out, and you'd actually have a displacement total of 0. So here they have a bunch of other vectors in figure 3.32, and they show them all scattered out. And the point of this sample that they show here in figure A versus figure B is just that if you added these together in either of them, you would still get the same resulting vector. Their location is really only relevant in their with respect to their orientation to each other. So if you were to stack these on the tails, or just take their totals independently like we have here, here, and here, you should get the same exact resulting vector, which is going to be an angle and a magnitude, or a magnitude and a direction. So this talks a little bit about finding the vector from its components, and I'll make a little separate video of this one so it's a little easier to find some of this info and you guys don't have to watch the whole video looking for it. So I'll make a third one and we'll be talking about finding a vector from its components.